Hey guys, welcome back. This is Coach Miller,
And Mr. Bunting.
and we're going to talk with you today about reaction stoichiometry. So we've talked a little bit about compound stoichiometry and counting the atoms in compounds. Now we're going to apply that to reactions where you have multiple compounds. First off, what we want to do is figure out what those coefficients mean in a reaction. So we've got an equation here. 2 moles of hydrogen gas react with 1 mole of oxygen gas to give you 2 moles of water. So what do they indicate? What do those coefficients indicate?
I think those coefficients indicate that 2 molecules of diatomic hydrogen react with 1 molecule of diatomic oxygen to produce 2 molecules of water.
Then that would be correct. So we've got 2 molecules of those gases, but those coefficients also indicate what?
How about 2 moles of hydrogen gas react with 1 mole of oxygen gas to produce 2 moles of water?
And that would be correct as well. So we have 2 molecules of hydrogen, but that 2, the coefficient, also represents the number of moles there. So take a look at this picture. You can see how all of that works together. 2 hydrogen molecules. We know that 2 hydrogen molecules will have a mass of 4.04, because remember, each hydrogen atom has an average mass of 1.01. Each oxygen atom has an average mass of 16. So if we add those together, you can see those would be 32. All of this works out together, and why this is important is our understanding of the conservation of mass, the law of conservation of mass.
Didn't we already study the law of conservation of mass?
Yes, we did, back in Unit 3, and we're going to look at that again in reactions because it's going to help us to understand what we start with is what we should end up with. So hopefully we remember that definition from Unit 3.
Can I see it again? Because I just don't remember. It's been a long break.
You know, yes, I think we have the definition there. So
How convenient.
mass can neither be created nor destroyed.
I've heard that before, but how does that apply to chemistry? I thought that was more about bombs.
Yes, bombs would be important, but in chemistry, there's a lot of chemistry in bombs as well. But in chemistry, with this unit in reaction stoichiometry, what we're doing is actually understanding that whatever mass we start with, we should end up with that same mass, assuming that the reaction completely goes its course or runs its course.
So it's kind of like the mass of the reactants is going to equal the mass of the products?
That's exactly right.
In a perfect situation?
In a perfect situation, your reactants, the mass of the reactant should equal the mass of those products. So here's an example. You got 2 moles of sodium nitride, and that breaks down or decomposes to give you 6 moles of sodium and 1 mole of nitrogen gas. Now, that's great. We understand moles. We can understand the whole counting process there. But if we start with 500 grams of sodium nitride, and that completely decomposes to give you 84.42 grams of nitrogen, how much sodium is produced?
I have no idea. Let's figure it out.
Let's do that. So if we have 500 grams to start with, then we should end up with 500 grams on the other side of the reaction, your products. So remember the conservation of mass. We cannot create or destroy mass. Okay, so if 84.42 grams of it is nitrogen, then how much of that will be sodium? How much of that remaining mass will be sodium? So if we start with 500 grams, we should have...
Sorry, it was awful.
That's all right. So if we start with 500 grams, and that decomposes, we know 84.42 grams is the nitrogen gas. So what portion has to be sodium? And in a perfect world, what we're looking for is simply the difference between 500 and 84.42.
So we can just subtract the mass of our reactants, 500 grams, from the mass of our product, 84.42 grams. And that's all we have to do?
That's it.
That seems pretty simple. I plug it into my handy dandy calculator. 415.58 grams of sodium.
And you would be correct. So when this reaction takes place, 84.42 grams of what you started with is actually going to be the nitrogen, and then the remaining 415, almost 416 grams is sodium. So that's an important piece of information, because when we start talking about theoretical yields and percent composition later on, you'll understand how all of this works.
Awesome.
So, some key things to think about. And the answer is already there for you, so you won't even have to think about this one. Stoichiometry calculations can go between any substance in a balanced equation. That means if I have a balanced equation like this one here, then I can go from moles of hydrogen to moles of water to moles of oxygen, and any combination there in that reaction.
That does seem handy.
Yes. So the cool thing about that is that you can start with oxygen and you can figure out how much water you could get. You could be given a mass of water and figure out how much hydrogen and oxygen you started with.
Awesome.
So just in case you wanted to synthesize water. Stoichiometry also allows us to predict theoretical yields. So it allows us to predict theoretical yields. And we'll talk about what theoretical yields are later on in this unit. But right now, what we're going to do is some examples showing you how these mole ratios work. So in this reaction, you've got 2 moles of hydrogen reacting with 1 mole of oxygen, and that produces 2 moles of water. So the question is, what is the mole ratio between hydrogen and oxygen?
Well, since we're talking about moles, the coefficients represent the moles, so I'm going to take that 2 for hydrogen and that understood 1 for oxygen and say it's a 2 to 1 ratio.
And that's exactly right. So 2 to 1. 2 to 1 would be my ratio for hydrogen to oxygen. What about hydrogen to water?
Hydrogen to water, you still have that 2 for the hydrogen. You also have a 2 for water. So you can say 2 to 2. You want to leave it 2 to 2, or do you want to? Or you can simplify that to be 1 to 1.
There you go.
Either way will give you the same answer.
That's right, because obviously dividing by the same number will give you 1. And that's important to know. Oxygen to water, what would be the mole ratio between oxygen and water?
Well, we have that understood 1 for oxygen and our 2 for water, so it's just 1 to 2.
Okay.
This is so easy.
Yeah, it's just a matter of looking at that balanced equation. So obviously it's important to write a balanced equation and be able to write these formulas correctly.
It's really important to know what the coefficients actually stand for.
Yes, it definitely is. You're not just trying to balance an equation, you're understanding that you're dealing with molecules or moles or whatever you're dealing with there.
I think I can fill up the rest.
Okay, so water to oxygen and water to hydrogen, you should be able to fill those out. We'll go ahead and write those in there for you, and continue working forward. And that's good work right there.
Thank you.
Use the balance equation. So here's a mole-to-mole problem, and we want to use this balance equation to go from one substance to another. we want to determine how many moles of water would form if you begin with 32.38 moles of oxygen gas.
This seems very similar to Unit 8, Coach Miller.
Yes, Unit 8, being able to use dimensional analysis and perform stoichiometric calculations.
Ooh,
big word there.
Fancy word.
So, again, I always like to start with what I'm given in the problem. So I start with 32.3 moles of oxygen gas, and it's important to write all of that down.
Do I have to write the units down?
Yes.
Okay.
Remember the rule in chemistry, no naked numbers. So always have the units. So 32.38 moles, and we're dealing with oxygen gas. Remember, oxygen is one of those diatomic molecules, right?
There were 7 of those, weren't there?
7 of them, yeah, and it actually makes a phrase. Remember, I bring clay for our new house, and those represent those 7 elements, right?
It also makes a 7 on the periodic table.
That's true. It does. It makes that pattern on the periodic table to remember those 7 elements. It's funny how chemistry just has all these patterns.
It just builds on itself.
Yeah, I mean, it's amazing how that works. So back to the problem. We have moles of oxygen, and we're trying to figure out how many moles of water we would produce. Well, looking at this equation, we know if I started with 1 mole of oxygen, I should get 2 moles of water.
Huh.
But I don't start with 1 mole of oxygen. I start with how many moles?
32.38 moles.
32.38. So I should get more than 2 moles of water. Would you agree?
I agree with that.
Okay. So the deal is now we want to go from moles of oxygen to moles of H2O.
Why would the O2 not be on the top of the line?
Well, remember, we always want to have like units on a diagonal so that they will cancel out.
Oh yeah. I remember that from Unit 8.
Yeah. So those will cancel, and when they cancel, I'm left with moles of water, which is what I'm looking for in my problem. Because we want to know how many moles of water I would produce. So based on this balanced equation, I know that for every 1 mole of oxygen, I get 2 moles of water. So now what you can do is simply take the number of moles that you start with, which is 32.38, and you multiply that by 2.
Okay. That seems simple enough.
Yeah, so let's plug that into the calculator and see what we would come up with. So 32.38, we're going to multiply that by 2, and that gives us 64.76. And remember, we're dealing with what unit?
We're in moles, Coach Miller.
Moles, and moles of what substance?
Water.
Very good. So there we go. There's a simple mole-to-mole calculation. We start with moles of one substance, and we can go to moles of any substance in that balanced equation. So we're going to build on that idea because, remember, we understand that we can go from particles, like atoms, or formula units, or molecules, to moles, and from moles to mass, which would be in grams. So now we have that extra mole-to-mole ratio, remember, to go from any substance in a balanced equation. So if I start with grams of a substance, I should be able to find grams of any substance in that balanced equation.
That'll be useful.
Yeah.
Do I need to memorize this chart?
It would be helpful to memorize this chart, yes.
Okay, I will do that.
So here's kind of a step-by-step process. If the question is how many grams of water could be formed by reacting 50 grams of hydrogen with oxygen, the first step, remember, we know that we're starting with 50 grams of hydrogen. So we calculate from grams to moles using the molar mass. So if I want to go from this substance here to this substance here, the only way to get there is what?
The mole ratio bridge.
The mole ratio bridge, that's right. So moles to moles.
So that's like converting from one element to another, or one compound to another compound?
That's exactly right.
Okay,
So that's my conversion factor that I would use in dimensional analysis.
okay.
So step one would be to find the molar mass. Then we're going to use the molar mass to find the number of moles, and then go from moles to moles to end up with my other substance, and then figure out what they're asking for. In this problem, they're asking for grams.
Okay.
So here's what the calculation would look like if we actually do this mathematically. So we start with 50 grams.
We always start with what's given to us, correct?
That's exactly right. 50. In this problem, we're given 50 grams of hydrogen, so I want to make sure we write all of that information down.
Since grams of hydrogen is in the top left, I should have grams of hydrogen in the bottom right.
You're
correct?
catching on.
Okay,
So
okay.
grams of hydrogen, and what are we trying to get to?
We're trying to get to moles, and we're given mass. So our conversion factor would be molar mass of hydrogen.
Molar mass of hydrogen. That's exactly right. So moles of hydrogen. Remember, molar mass is the number of grams in how many moles?
1 mole.
1 mole. So how many grams of hydrogen would be in 1 mole?
2.02.
Very good, 2.02. Remember, we get those values from the periodic table. Each hydrogen is 1.01 by itself. Now that we have moles of hydrogen, we can do what?
Do our mole ratio bridge. So we need to change from hydrogen to water. And since H2 hydrogen is in the top left, we need to keep hydrogen in the bottom right. We're going to water, so we need to put moles of water on top.
Very good.
I'll catch it on.
So now we can really forget everything to the left over here and just look at this particular box or this square. What is the relationship between moles of water and moles of hydrogen?
Well, if I look at our coefficients, I can see that we have 2 moles of hydrogen for every 2 moles of water. So we
Very
could
good.
say 2 over 2 or 1 over 1.
Or 1 over 1. So why don't you take it over here and
I'm going to go ahead and simplify it and just say 1 over 1 because that makes math really easy.
okay. But in the problem, we want to know how many grams of water that we could produce.
So I'm not done yet. So I have to go from moles of water to grams of water. So if I have moles of H2O up here, I need to have moles of H2O down here. And I want to end up in grams, so I'll have grams of H2O on top.
Looking good so far.
So my conversion factor would be molar mass again. So that's how many grams are in every 1 mole. There are 18.02 grams in every 1 mole of H2O. 16 from the oxygen, 2.02 from both of the hydrogens.
Okay, great. So right now we have the unit and the substance that we're looking for at the top right. Grams of water. So we can simply multiply everything on the top and divide by everything that's on the bottom. So we're dealing with 50 times 1 times 1 times 18.02. And I'm going to divide that all by 2.02 times 1 times 1, which we know is simply 2.02. And that will give me the number of grams of water that I can produce if I start with 50 grams of hydrogen gas.
What is-
And that value is 446 grams.
That seems like a lot of work.
Yeah, a lot of steps, but if you're in the lab, those steps are important because you can kind of predict what you're going to get, and you can know, okay, what substances do I not need to put together, which is a good piece of information to have
Okay.
going into the lab. So we're going to work out the next couple of examples and just show you the work. But this would be a good time for you to pause and maybe try those 3 or 4 practice problems yourself, and then come back and check your work with us.
Discard.